133. Gray without a calculator. So if I'm doing 33, I'm going to look at places. I would say this would be I'm going to say if it's rational, you wouldn't need a calculator. But because of this square root, because it's a radical also, you would probably need a calculator to see this. What is it, a corner on it if you grasp it? Grasp it. Did you look at it? Not sure why this one is in this section though. I know. That's supposed to mean no calculator, but I would argue you would need. Yeah, but if you're finding the derivative, but this is saying all values of x where it's differentiable, so you have to check for asymptotes, corners, and cusp. You see what I'm saying? So yeah, we can find the derivative of that. So 1 plus x squared, right. See what this looks like. So when you graph this, it does something like that. But because it's a radical function, it's a dead stop right here, right? So there's no corners or cusp or anything like that on here. My bottom's never going to be 0 because if you're adding x squared to it, right, you're always going to be adding a positive number to 1. So that's never going to be 0. Could I ever have a negative number under here where it would be imaginary? Well, that's where this is coming. I guess that's what they wanted you to do. I would say that's a calculator question. If I were asking you where is it differentiable. Now, if I asked you what is the derivative, I would say you could definitely do that without a calculator. But for this one, where is it differentiable? It's differentiable everywhere x is less than whatever this value is, which looks like it is 1. Not like that. No. You may have to find the derivative of something like that, but as far as differentiability, if you're looking at differentiability like that, if it's something where vertical tangent, corner cusp, that kind of stuff, you have to calculate. Yeah. Yeah. Oh, okay. I forget. Y'all have to stay on me. All right. Here I'm just finding derivative. So derivative here, I'm going to do 1 over 1 plus e to the x. And now I'm going to chain it. So I know why y'all. What's the derivative of the chain? Yeah. So e to the x over 1 plus e to the x. Can't really do anything else with that one. Which one did you say, Madison? Yes. 21, you would have to use logarithmic differentiation. And unless that's specified, you may not realize that. On your test, I will tell you if you have to use logarithmic differentiation because you don't have enough tools to do this without that. But let's go ahead and log both sides. So you get the log of y equals the log of x to the log x. And the reason we log here, we can get this, we can rewrite this. So I get log of x times log of x, which is really just right that way. So now whenever I take the derivative, I've got 1 over y, but because I took the derivative of y, I need to follow it with what? dy dx. And then I'm going to do power, so 2 times the log of x, and then I'm going to chain, so derivative of log x is 1 over x. Multiply both sides by y, so I got dy dx equals y times 2 over x log x. And what is y? What did we start with? I don't remember what number. X to the ln x. So this would be x to the log x. I got a 2 and I got a log x still up top. The only thing in bottom is the x. It's like y over 1 ln over 1. Welcome. Yeah. 27. What'd you ask for? I do 27 then hit 57. 27 y equals, what's wrong? Yeah. This is y equals z inverse cosine z minus the square root of 1 minus z squared. So derivative here, it looks like a product rule in the first two. So derivative of the first would just be 1 times the second plus the first, and then derivative of inverse cosine is what? I don't know that off the top of my head. Negative 1 over, so that's straight off of your green sheet. Minus, and again, you already know what I'm going to do here. I'm going to change that to 1/2 exponent. So I get 1/2 times 1 minus z squared to the negative 1/2, and then I have to chain it, so it needs a negative 2z. And now I can just kind of clean everything up. I get the inverse cosine of z minus z over square root of 1 minus z squared. Those are going to cancel, but I've got 2 negatives, so it's going to make me have a positive. I've got a z up top. I've got a 1 minus z squared on the bottom. These are the same. They're already the same denominator, so I might as well just combine them. Inverse cosine of z minus 2z over square root of 1 minus z squared. I don't know how they formatted their answer. I would stop there. If it were me. Oh, no, stop. Nobody caught that. Those cancel. It's just inverse cosine z. But look at what it equals. That is, they just got in a different order. That's, these canceled. Yeah. You said 57 so? Ooh. Determine if the function is differentiable, continuous but not differentiable, and neither continuous nor differentiable. And this is a calculator problem. So let's think about what those definitions. I like that they add these. We keep coming back to these kind of problems because you don't want to forget these definitions. All right, I'm looking for differentiability. I'm looking for continuity. And really that'll tell me because it wants to know are they continuous and or differentiable or neither or both. So how do I determine if they're differentiable? So that's with your continuity. But yes, the limits have to be the same. But if I look at the derivative, I need to look at the function, right? But I also need to look at the differentiability from the left and the right. Right, right. So I need there not to be any discontinuity. So let's check continuity first. How about that? Let's check continuity. So remember, continuity means the limit from the left equals the limit from the right, which also equals the value if you plug in at that particular value. And the only place I know that this is going to be a continuous function, I know this is linear, that's going to be a continuous function. So where I'm looking is at this value right here. Square root of x, it's just a radical function. It could. What you got? Okay, hold on just a second. I'm gonna finish this one. Um, what? Yes. All right. So how do I test the continuity at 1 here? So I'm gonna do the limit. Well, I do plug in 1. I'm gonna do f of 1 here from the left, and then f of 1 from the right, and see if I get the same thing. Here, if I plug in 1, I get the square root of 1 squared plus 3, which is the square root of 4, which is 2. So that's the limit actually as I approach 1 from the left. So that's 2. And then as I approach 1 from the right, that's the second equation, right? So that would also give me 2. And what does f of 1 equal? Well, because it is defined right here, when it equals 1, then this is the one I plug into, okay? Now realize if there wasn't that line under there, what would happen at 1? Close. It's another type of discontinuity. There'd be a hole there, right? If the limit's the same from the left and the right, but then it doesn't include that actual point, it's an open dot there, so it'd be like a hole. But here, it does include, so f of 1 is 2, so therefore I am continuous on my domain. And I have to make sure I say on my domain, because my domain runs from -1 to 3. Obviously, it's not continuous past that because it doesn't go on forever. But from -1 to 3, I am continuous. How about, what's the second part asking? That's for, okay, I haven't looked at differentiability. Right now I just looked at continuity. So really I answered part, well, I haven't really answered anything because this is continuous and not differentiable. Okay, so because this is a calculator problem, you said, how do I know about this one? So I'm going to graph and see what that looks like real quick. So I'm going to go into y equals, and I'm going to do the square root of, well, right now, no, there's not a hole because of the line under it. Okay, but let's look at the derivative from the left and the right first. Let's do that because I looked at continuity. Now let's, because it said is it differentiable? So if it's differentiable, the limit from the left has to equal the limit from the right, and it has to be continuous. I know it's continuous, so now let's look at the derivative from both sides. Does that make sense? No, it doesn't. Well, you tell me. Where do you? Yes, yes. So if I want to know what is the left-hand derivative, right? You don't like this problem? The left-hand derivative is going to come from this equation because it's coming in from the left. So I want to know what is f prime of, remember the point in question is this 1 right now, right? I want to know the derivative at 1 here. So find the derivative of this first. So 1/2 x squared plus 3 to the negative 1/2, and then chain it. So x times x squared plus 3 to the negative 1/2. And now I'm just going to plug in 1 here. So 1, 4 to the negative 1/2. What's 4 to the negative 1/2? 1 over 2. That's okay. So 1/2. So my left-hand derivative, because I'm coming in from the left side, is 1/2. So if my right-hand derivative matches that, then I know it's also differentiable on its domain. Y'all okay there? Okay. Okay. Right-hand derivative. Well, that one's a little bit easier, right? So the right-hand derivative is just 1. It's always 1. It's constant. So as I compare these two, they're not the same. So what does that tell me about this function? That it's what, but not what? It's continuous on its domain, but it is not differentiable on its domain, right? So part A says, where is the function differentiable? Everywhere, but its domain is not everywhere. So where is it differentiable? It starts at -1, right? And it includes it. And then I have to leave out this 1 because it's not differentiable there. The left-hand derivative and the right-hand derivative are not the same. So I'm going to stop at 1, yes? And then it's differentiable everywhere else. Does that make sense? Do y'all see how we found it? Yeah, you would. You would now. How about continuous but not differentiable at 1? So the only place I'm not differentiable, bro, don't look up after I explain this whole problem for 20 minutes and then like. So B is x equals 1, right? So where is it? Because we said it's not differentiable, but we said it's continuous on its entire domain. So then part C is neither continuous nor differentiable. Well, we know it's always continuous, so it's nowhere. We held off on that kind of domain right now. Which one? Oh, okay.
It'll be like 1 over yada yada, and then it'll be comma p greater than.
They're just restricting. Which number are you looking at? This game? They're just restricting whenever you have like a 0 in the denominator because you can't have it's right now focus on finding the derivative. We're gonna focus on that a little bit later. Camden, you said 29. Inverse cosecant of secant, and it says I'm between 0 and pi over 2. All right, so I just want to find the derivative here. Am I evaluating at a certain point? Find the derivative of the function. All right, so derivative. Cosecant, the inverse cosecant is -1 over the absolute value of x times the square root of x squared minus 1. Right? Oh, come on, Stacy. As I fill this in, this is your x. Okay, that's your x to start with. I'll go back and chain it in just a second. So 1 over the absolute value of secant x times the square root of secant squared x minus 1, right? So that is that times, and now I need to chain it. What's the derivative of secant x? Because I'm defined already in just quadrant 1. That's 0 to 2 pi, right? So I'm right here. Secant is 1 over cosine, and cosine's always positive there anyway, so the absolute values are not going to make that much difference, because if you take the absolute value of a positive number, it just stays the same. So I say that because this is really over 1. These secants can cancel out. Well, it's just multiplied by that, so you can put anything over 1 like that. So now I have tan x over the square root of secant squared x minus 1. I would probably stop there. Did they not stop there? 29. Yeah, that's... I wouldn't go any further than that. Yeah. Yeah. 41 y cubed plus y equals 2 cosine x. So a little implicit differentiation here, but it asks for the second derivative, so here we go. 3y squared dy dx plus dy dx equals 2, negative 2 sine x. And I'm just going to manipulate this a bit and solve it for dy dx. Dy dx 3y squared plus 1. And now second derivative. All right, here we go. Second derivative. You will have a second derivative implicitly on your test. So let's... All right, derivative of the... I would use chain here. I mean quotient. It may not be this involved, but you'll have a... All right, derivative of the top, negative 2 cosine x times the bottom minus the top, so I'm going to change it to plus, times derivative of the bottom. So I got 6y dy dx all over the bottom squared. This looks a lot worse than what it really is. So now I need to replace dy dx with that. Negative 2 cosine x times 3y squared plus 1 plus 2 sine x times 6y times negative 2 sine x over 3y squared plus 1. Oops, crap, screwed up. We'll see what happens. I might make this negative 6y squared plus 2 times cosine x. I'm going to make this negative because of this negative. We'll go straight across. 4 sine squared x. Nope, it's not 4. 24y. Bless you. 24y, that takes care of that one, and that one. Sine squared x over 3y squared plus 1. I'm going to do that. I don't know that I would keep going on this unless I was specifically asked to simplify it. They did. I mean, I'll be happy to. You want me to keep going? It'll be fun. Negative 6y squared plus 2 cosine x. I'm going to multiply this one by a 3y squared plus 1 to give them the same denominator. All over 3y squared plus 1. But I'm also going to multiply it by the reciprocal of the bottom. I would most definitely stop here. You said 61C? A differentiable function f has the property that the derivative is greater than 0. The line y equals 3x minus 2 is tangent to the graph where x equals 2. What'd you get for your slope for that one? For A. What you said I needed A and B to find C? And then for B, now if you need me to work it, I will, but if you don't need it, okay. M should be 3, right? Oh, it's inverse. I'm sorry. Okay. All right. So then find the equation of the line tangent to the graph y equals f of x over x at the point where x equals 2. This is just seeing can you find f of x over x tangent at x equals 2. I'll find the point first because it seems to be the easiest. So y of 2 is going to be f of 2 over 2, right? And so I find that f of x. Do I have that f of x anywhere? Yeah. 3x minus 2. Yeah, right. If you plug in 4 to that initial, y equals 3x minus 2. That'd be 6 minus 2, which is 4, over 2, which is 2. So this point is 2, 2. So now all I need is a slope, right? Because that's what it means to be tangent. So what is the slope? Because it defined this as being f of x, which I'm assuming is the original equation. It's a little confusing with the way that they worded it. But yeah, I would say that's your original equation because that's what you've been referencing the whole time. And then they've just created a new function by dividing it by x. So the slope here would be the derivative at 2. So I'd have to use quotient here, right? Derivative of the top. Which one? It's a different function because now your function is all of this divided by x, right? So derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. And I would just plug that 2 in here. And this is where you probably need the a and b part, maybe, over 2 squared. So what's the derivative of f at 2? So that's your original. When they reference f in this problem, they're talking about that original 3x minus 2. So what's the derivative at 2? So this is f. So what's f prime of 2? It's just 3. So I'd get 3 times 2 minus, well, what's f of 2? Yeah. Did I mess up? Oh. 4 again, right, over 4. So 6 minus 4, 2 over 4, which is 1/2. Again, that's my slope, right? So I've got the 0.22, the slope 1/2, so y minus 2, 1/2 x minus 2. Yes, ma'am. Which one are you looking at? Oh, nope, skip 49 and 51. Those are, that's our parametrics. I'm sorry. Sorry. Parametrics aren't hard. They're just BC. Huh? 49 and 51. Odds. Yeah. Yeah. $49 and $51. This is a typical calculus multiple choice problem. They love a table and they love asking you to analyze that table every which way to tomorrow. Find the first derivative of the following combinations. So this is kind of like the one we were just doing. It says the square root of x times f of x when x equals 1. So I'm just going to use product rule here, okay? Again, I'm going to make this 1/2. So the derivative would be derivative of the first times the second plus the first times derivative of the second. And then they say do that when x equals 1. So 1, 1, 1, 1. And then I'm going to use the table, right? I got 1/2. 1 to the negative 1/2 is just 1. What's f of 1? Oh. You sure? F of 1 is -3. 1 to the 1/2 is 1. And then the derivative at 1, so this time I'm coming over here, times 1/5. And whatever that comes out to be. -15 plus 3, so -15 plus 2. -13 over 10. Yes. Yes. Think about those corners and cusps that look like this. They're continuous but not differentiable. That's okay. Yes. Yes, ma'am. For 29. Let me find 29. What do you mean, a -1? Okay, so are you saying like that? Like you did the derivative like that? Oh, this is like that. Oh, I'm sorry. Yeah, it would just make the answer negative. Sorry. Yeah. And then this, so this is the chain, right? That's the derivative of the inside here. And the reason I could mark out a secant on the top and the bottom, even though that was in absolute value, but it says absolute value, but if you think about, it already tells me that I'm between 0 and 2 pi, right? Secant is 1 over cosine. Cosine is your x value, right? If I'm between 0 and 2 pi, here, x is always positive, right? So it's never going to be negative. So on this domain, the absolute values are really irrelevant. So it lets me cross them out. Yes, ma'am. Yeah. 37. Find dy dx. So I am going to start by making this 1/2 exponent. 1/2 times xy to the negative 1/2, and now I chain. So the derivative in here, I'm going to have to do product rules. So derivative of the first times the second plus the first times the derivative of the second equals 0. This is actually going to be 1 over 2 times the square root of xy. And then I'm multiplying by all of this, so all of this is in the top. Y plus x dy dx equals 0. If I multiply both sides by 2 times the square root of xy, I get y plus x dy dx equals 0. I can subtract y, and I can divide by x. So let's find the tan line and the normal line when x equals 3. So I'm going to do slope. I'm going to do derivative first. Minus 2x to the negative 1/2. Now I'm going to chain it. So 2x minus 2. So let's play with it just a little bit, right? Let's do 2x minus 2 is up top. I've got a 2 and a square root of x squared minus 2x in the bottom. I could technically take a 2 out of here, right? And then cancel top and bottom. So I'd end up with x minus 1 over square root of x squared minus 2x. Is that the equation of their tan line? No, because that wouldn't make sense. 2x minus 2 is the chain. That's right. Their derivative, that's what I have. Look, if you do this, this is, so 1/2 times, this would put this in the bottom, 1 over x squared minus 2x to the 1/2. And then your chain is 2x minus 2. That's exactly right. So 1 over 2 square root x squared minus 2x, and then the chain is 2x minus 2. Which one did you say, Stella? Which one did you say? Yes, to find the slope. Yes. Now, 66D is f of 1 minus 5 tan x, and x equals 0. Find the first derivative of the following. This is just a chain. This is seeing if you understand chain, right? So this is a composition function. It's just, here's your g of x, and they've already plugged it in there. So I'm going to do the derivative of f. But remember, you leave all that, oh, great day. And now I'm going to chain it. So what's the derivative of all this? -5, what's the derivative of tangent? Secant squared, like that. So now I look, where did it say? It said it's 0, so I'm going to put a 0 in here. So this is f prime of 1 minus, what's the tangent of 0? 0. So 1 minus 0 times -5. What's the secant of 0? Secant is 1 over cosine. So what's the cosine at 0? 1. So I've got derivative f prime of 1, and then I'm going to multiply it by -5 when I'm done. So look at that chart. F prime of 1 is 1/5. And when I multiply that by -5, I get, yeah. Do you have a?
Is that the same? That's the same thing, right?
Y plus 2 over x. Yes. Yes. What's your question, Robert?
I remember like putting them so they're like, how do you even do differential? I don't know if I did that.
Well, that's the ones that I was telling you. You need to probably look at the graph on them. Look at places where they differentiable means it's continuous and there's no corners, cusp, or vertical tangents. So a natural log is not going to have those. But if yes, just graph them. That's the easiest thing to do on those. I won't give you any quite like that.
But it says like calculator.
That's not right. You are struggling with 66. All right, guys, if I am working harder than you, that is a problem. Several of you have not done anything since you have been in here. All right, if I do 66E, if I do... Okay, tell me what you did. Didn't say find the derivative? Find the derivative of this. Oh, you're doing... Since it's a function and a function, I would go ahead and do quotient. Okay. Okay. Times the bottom. I know what you meant. Okay, keep going. Okay. If we are just evaluating, when I get to this point, I'm going to go, hold up. I'm not going to try to manipulate. I'm not going to try to simplify because I am evaluating and I know what I plug in. I'm going to plug in now. I am not going to do any more work than I have to do. And trying to manipulate this would be terrible. I'm just going to plug in because these are easy. Sine of 0, cosine of 0, f prime. I've got a chart for those. All right, this is in your chart. What is it? 2 plus, what's the cosine of 0? What's the sine of 0? Is 0. What's f of 0? Look in your chart. It doesn't matter. You're right. Irrelevant because it's 0. Over 2 plus, what's the cosine of 0? Which is Not bad, is it? Oh my gracious.
Looking at it, it's making me shaky.
Why? Okay. 10 sine pi x over 2. It's okay. Tell me where you think you start. Possibly. What are you trying to plug in? What do you think you plug in here, or when do you think you plug in here? That's what I would do too. Then you're going to replace every single x. Watch what we do.
10.
All right. Okay. And you see that this is a product, right? Okay. Okay, so derivative of the first. And then I chain it. What's the chain? Close. So that's derivative of the first. Now, f squared of x like this is the same thing as this. Times the second. I'm going to write it this way. I think it'll be a little easier for you to see. Plus, you do yours so backwards than me. Okay, derivative of the second. What's the pink sheet? Oh, yeah. Derivative of the second. So 2f of x, but don't forget to chain. What's the derivative of f of x? Because remember, I do power and then I do inside. Because that's why I wrote this like this so you could see it. So I do power first, but then I have to take the derivative of what's inside. So when you do power, you leave the inside alone, but then you have to take the derivative of what was in there. Yes. Yes. All right, this is all derivative of the second, right? Times the first. This looks bad, but really remember, I'm just writing as is and I'm not doing any manipulation. So now I'm just going to go in and replace all my x's with a 1. What's the cosine of pi over 2? 0, right? I'm up at the top of the circle. That's 0. None of this matters because I'm multiplying to 0. Plus 2 times, what's f of 1? That's in your chart. -3. What's f prime of 1? 1/5. And what's the sine of pi over 2? Again, up at the top of the circle. 1. So I've got 10 times -6 over 5, which should be -12. Please, for the love of everything good, tell me that's what they got. I don't know. What letter says F? Whew. That was a good one. A little tricky. That's why we're practicing with these kind. Look, if you struggle with 66, I don't know, did I give you 67? I was going to say you need to do 67. I didn't know if I'd given it to you or not. I wanted to give it to you. What you got? Either one of you. I don't know which one. 37? I just did 37. So at this point, you really could have divided by this on both sides and just been left with y plus x times dy dx equals 0. You could come here and divide by 1/2 xy to the negative 1/2. Cancels out here, and over here it's just 0. Then it's easy to get dy dx by itself. Yes, ma'am. 39 is another second derivative. Joyce, are you done with that? Or you still need it? Okay. X cubed plus y cubed equals 1. So let's do first derivative first. 3x squared plus 3y squared dy dx equals 0. And I'm just going to solve for dy dx. And I think the first derivative is pretty easy for you guys. It's whenever you get to the second that you start struggling. I'm going to divide by 3y squared. I get negative x squared over y squared. Now second derivative. And I'm probably going to do this. Derivative of the first times the second plus the first times the derivative of the second. So negative 2y negative 3 dy dx. And of course, this is second. I need to replace this with this. And then I'll start cleaning it up a bit. Negative 2xy negative 2. I got two negatives. Those are going to cancel, so I'm still going to be plus. Actually, I lied because this is negative x squared y negative 2. So I'm going to be minus. I got 2. I got x2. x2 would give me x to the 4th. Y negative 3. Y negative 2 would give me y negative 5. I'd probably stop there. I mean, you could go through technically and find a common denominator if you wanted to. I probably would not. It's mine. Yes. I did 37. No, I didn't. I did. So when I just showed Joyce that I just.
Everybody, you know,